Some worlds look safe only because they are familiar. The moon is the brightest object in the night sky after the sun. It rises over cities, oceans, deserts, farms, and empty roads. It has watched every human civilization appear beneath it. It is close enough that we can see its dark plains with our own eyes. Close enough that 12 people have walked across its dust. Close enough that radio signals can cross the distance in a little more than 1 second. And that closeness can fool us. Because the moon is not a gentle stepping stone waiting beside Earth. It is not a quiet desert where we simply need to build domes, plant flags, and slowly turn it into a second home. It is a dead world with no breathable air, no weather to soften the surface, no oceans to store heat, no magnetic shield above the ground, no living soil under your feet, and no forgiving environment outside the walls. On Earth, a broken window is an inconvenience. On the moon, it can become an emergency. On Earth, dust is annoying. On the moon, dust can cut into seals, coat machines, and follow astronauts back inside. On Earth, night is just a few hours of darkness. On the moon, night can last about 2 weeks, long enough for heat, batteries, and patience to run down together. So tonight, before we imagine cities under glass, glowing bases near the lunar South Pole, or families watching Earth rise above the horizon, we have to ask a harder question. Could the moon really become a home? Or would it always remain a place where humans are only barely surviving? Before we begin, if you enjoy calm space documentaries like this, subscribe to the channel, leave a like, and write a comment telling us where you are watching from and what time it is for you right now. It is always fascinating to imagine people listening from different places on Earth, under the same moon, at completely different hours. Tonight, you are watching the Space for Sleep channel, talking about the terrifying problem with colonizing the moon. And the problem begins with the thing that makes the moon so tempting in the first place. It is close. Compared with Mars, Jupiter, Saturn, or the nearest star, the moon feels almost local. Light from the moon reaches Earth in just over 1 second. A spacecraft can make the journey in days rather than months. If something goes wrong, Earth is not a pale dot lost in deep space. It is a blue world hanging above the horizon, visibly there, heartbreakingly near. That nearness is why the moon keeps returning to human plans. It is the first place we reached beyond Earth. It is the most obvious place to practice living away from our planet. It has no atmosphere to fight during landing. Its gravity is weak enough that launching from the surface is easier than launching from Earth. Its rocks may contain oxygen locked inside minerals. Its polar regions may hold water ice hidden in cold traps. Its far side could be useful for radio astronomy, because Earth's radio noise is blocked by the moon itself. All of that sounds like the beginning of a permanent future. But every advantage has a hidden cost. The lack of atmosphere makes landing easier in one sense, but it also means there is no air to slow a spacecraft down. Every landing must be handled by engines, fuel, navigation, and timing. The weak gravity makes launching easier, but it may not be strong enough to keep human bodies healthy for years. The water ice could be useful, but most of it is not sitting in easy lakes or rivers. It is trapped in dark, frozen places that may be among the coldest environments in the solar system. The moon is close enough to reach, but not close enough to become safe. That is the first trap in the dream of colonizing it. Distance is only one part of survival. The deeper challenge is not reaching the moon. It is staying there after the dramatic landing is over, after the cameras turn away, after the first week becomes the first month, and after a base has to keep working through heat, darkness, dust, radiation, loneliness, and mechanical wear. A real colony is not a flag. It is not a single habitat. It is not one successful mission. A colony is repetition. It means waking up there again and again, repairing systems that were never supposed to fail so soon, replacing filters, cleaning dust, checking seals, growing food, reusing water, watching radiation forecasts, keeping batteries alive, training new people, raising the possibility that someone might be born there, grow up there, and have no memory of standing under a blue sky. That is when the moon stops being a destination. It becomes an environment, and the environment is the problem. The first and most obvious danger is the vacuum. On Earth, we rarely think of air as machinery. It is just there, pressing gently against every part of us, filling our lungs, carrying sound, spreading heat, lifting clouds, and protecting us from the emptiness above. The atmosphere is so constant that it feels invisible, like the default condition of existence. On the moon, that default is gone. The lunar surface is not surrounded by breathable air. It has an extremely thin exosphere, a faint scattering of particles so sparse that it does not behave like an atmosphere in any normal human sense. It does not let you breathe. It does not carry weather. It does not soften temperature swings. It does not stop tiny meteoroids from hitting the ground. It does not protect a person from space. For a colony, that means every habitable room is a pressure vessel. A bedroom is not just a bedroom. It is a container holding atmosphere against a vacuum. A hallway is not just a hallway. It is part of a life support system. A greenhouse is not just a greenhouse. It is an artificial pocket of earth chemistry sealed inside a dead world. Every door, wall, pipe, cable port, hatch, and window becomes part of the line between life and the outside. That line has to hold every hour. It has to hold when the structure warms and expands under sunlight. It has to hold when the same structure cools and contracts in darkness. It has to hold after dust scrapes against seals. It has to hold after micrometeorite impacts. It has to hold after years of vibration from machinery, rovers, pumps, drills, and people moving through the base. The terrifying part is that a lunar colony could be destroyed by something that looks small. Not a giant asteroid, not a huge explosion, not a dramatic science fiction disaster. A cracked fitting, a damaged airlock seal, a pressure sensor that fails at the wrong time, a dust-contaminated hatch that does not close fully, a micrometeorite puncture in a line that was supposed to last for decades, a software error that opens the wrong valve, a maintenance routine skipped because the crew is tired. In an atmosphere, small leaks are often manageable. On the moon, leaks are moral alarms. A slow loss of pressure might give a crew time to respond. A fast breach could force them into emergency suits, seal off compartments, and decide within seconds which part of the habitat can be sacrificed. That is one of the differences between visiting and living. Apollo astronauts could accept short-duration risk. They landed, worked, collected samples, returned, and left. A permanent settlement cannot live forever under mission mode intensity. It has to become ordinary enough for people to sleep, cook, argue, fix equipment, exercise, and relax. Yet the environment never becomes ordinary. The vacuum is always waiting on the other side of the wall. Imagine a lunar morning inside the habitat. Outside, no wind moves across the plains. No birds, no traffic, no ocean in the distance. The surface beyond the window is bright but silent. Earth hangs above the horizon like a painting someone forgot to remove. Inside, fans are moving air, because air will not circulate naturally in a sealed habitat unless machines push it. Carbon dioxide scrubbers are working. Humidity control is working. Oxygen levels are watched. Pressure readings are logged. A person eating breakfast is alive because an entire artificial atmosphere is being manufactured around them. If the fans stop, air becomes uneven. If carbon dioxide removal fails, the danger is invisible at first. If oxygen supply becomes contaminated, the body may not notice until judgment is already impaired. If pressure drops slowly enough, the crew may feel tired, confused, or headachy before the alarm explains why. That is the strange horror of lunar life. The moon does not always attack loudly. Sometimes, it simply removes one invisible requirement at a time. Air is the first requirement. Pressure is the second. Temperature is the third. Clean water, stable power, food, waste removal, radiation shelter, and medical care follow behind. On Earth, nature provides many of these in rough form before technology improves them. On the Moon, technology provides nearly all of them from the beginning. This means a lunar colony would not be a city in the way we understand cities. It would be closer to a spacecraft spread across the ground. Every building would have to behave like a spacecraft. Every farm would have to behave like a spacecraft. Every workshop, sleeping area, medical room, storage unit, and scientific lab would be part of a sealed system. Even a simple walk outside would require planning, clothing, communications, oxygen, cooling, power, dust control, and a route back. The moon is close to Earth, but it is still space. And the first terrifying problem with colonizing it is that the outside is never survivable. The second problem is temperature, and it is easy to underestimate because the moon looks so still. From Earth, the lunar surface appears calm. Its craters do not shift like clouds. Its mountains do not glow with storms. Its plains do not show seasons the way continents do. But stillness is not comfort. A world can look quiet and still be violently extreme. The moon has no thick atmosphere to carry heat around. Sunlight strikes the surface directly. Shadowed ground loses heat directly into space. There are no oceans to store warmth, no winds to soften the boundary between hot and cold, no clouds to scatter sunlight, no weather systems moving energy from day to night. So the surface behaves like exposed stone under an unforgiving sky. In sunlight near the equator, lunar temperatures can rise high enough to cook electronics, soften materials, stress seals, and turn an unprotected habitat into an oven. In darkness, the same surface can fall to temperatures colder than anything humans normally experience on Earth. In permanently shadowed craters near the poles, temperatures can fall even lower, into a deep freeze that can preserve ice but punish machinery. This creates a basic engineering nightmare. A lunar base has to survive both heat and cold, often in cycles that last far longer than a normal day on Earth. A full lunar day-night cycle is about 29.5 Earth days. In many places, that means roughly 2 weeks of sunlight, followed by roughly 2 weeks of darkness. The temperature does not merely change from afternoon to evening. It can move from harsh solar heating to deep radiative cooling for days at a time. For humans, this is not just uncomfortable. It changes everything about the design of the colony. During the long day, solar panels can produce power, but habitats and equipment must reject heat. Computers, batteries, pumps, people, lights, and machines all create waste heat. On Earth, heat can be dumped into air or water. On the moon, the only real way to lose heat to the environment is radiation. Radiators have to face space. They have to avoid absorbing too much sunlight. They have to work while dust tries to coat them. During the long night, the problem reverses. Solar panels produce nothing without stored energy or some alternative source. Equipment cools. Batteries lose efficiency. Mechanical parts contract. Liquids can freeze if not protected. Habitats need heating, not cooling. The same base that struggled to get rid of heat may now need to conserve every watt. A colony cannot simply turn off for 2 weeks. People still need oxygen, Water still needs to circulate. Food still needs to be preserved. Computers still need to monitor pressure, radiation, power, pumps, and communication links. Medical equipment has to remain usable. Greenhouses may need light. Batteries have to stay within safe temperatures. Rovers parked outside might need heaters just to survive until the next sunrise. This is why the lunar poles are so attractive. Near some polar regions, sunlight can remain low on the horizon for long periods. Certain high areas may receive more frequent illumination than equatorial regions. Nearby permanently shadowed craters may contain water ice. That combination, sunlight for power and ice for resources, is one reason the South Pole appears so important in future plans. But the poles are not easy. The sun stays low, creating long shadows that can hide hazards. A small crater rim can cast darkness across terrain. A rover may move from bright glare into black shadow where cameras struggle and temperatures drop. Communication lines may be blocked by terrain. Landing sites may be uneven. Permanently shadowed regions are not comfortable ice mines. They are dark traps where temperatures can be unbelievably low. Imagine trying to build infrastructure there. Solar arrays must be placed where they see the sun, often enough to matter. Power cables must run across rough ground and survive dust, cold, micrometeorites, thermal contraction, and human or robotic maintenance. Habitats may need to be close enough to resources to use them, but far enough from dangerous terrain to remain safe. Mining equipment must operate in shadow or near shadow, where ordinary lubricants, batteries, sensors, and metals can behave differently. That is the pattern of lunar colonization. Every solution creates its own second problem. Go to the equator, and you get simpler lighting geometry, but worse day-night extremes and less accessible polar ice. Go to the poles, and you improve the resource argument, but inherit low sun angles, long shadows, difficult terrain, and brutal cold traps. Build on the surface, and you get easier access and construction, but more radiation, temperature stress, and micrometeorite risk. Build underground, and you gain protection, but excavation, access, power routing, and emergency evacuation become more difficult. There is no easy place on the moon. There are only different kinds of hostile. Then comes the energy problem. A lunar colony is, at its core, an energy machine. It turns power into air, warmth, water recycling, communication, food production, lighting, construction, computing, medical care, and motion. Without energy, the base stops being a settlement and becomes a sealed shelter counting down. Solar power is the obvious first answer, because the moon has no clouds, no rain, and no atmosphere to weaken sunlight in the same way Earth does. In direct daylight, solar panels can work well. They are relatively simple compared with nuclear reactors, and they fit the dream of a clean lunar base quietly collecting sunlight. But the moon punishes simple answers. For much of the surface, night lasts about 2 Earth weeks. That means a solar-powered base needs either enormous energy storage, a secondary power source, or a location where sunlight is available far more often than average. Batteries for a small mission are one thing. Batteries for a permanent settlement are another. If the colony includes habitats, laboratories, farms, workshops, rovers, mining equipment, communication systems, and emergency reserves, the storage requirement becomes massive. And batteries are not magic. They have mass. They age, they lose capacity, they need temperature control. They can fail. They need to be launched from Earth or manufactured locally. And local manufacturing on the moon would itself require energy, mining, processing, quality control, and machinery. So the 2-week night becomes more than darkness. It becomes a test of civilization. Can the base store enough power to keep air moving, water flowing, carbon dioxide removed, temperatures stable, and people alive until the sun returns? Can it do that after years of degradation? Can it do that after dust reduces solar panel efficiency? Can it do that after one battery bank fails? Can it do that while a medical emergency, a rover rescue, or a construction accident demands extra power at the worst possible time? This is why nuclear power enters the conversation. A compact nuclear system could provide steady energy through day and night. It would not care about shadows. It would not shut down when dust covers panels. It could keep habitats warm during darkness and support mining operations in polar regions where sunlight is difficult. For a serious long-term settlement, nuclear power may not be optional, but nuclear power on the moon brings its own complications. Reactors must be transported safely. They must be assembled or deployed with high reliability. They must reject heat into vacuum. They must be placed far enough from habitats to reduce radiation concerns, but close enough that power transmission remains practical. They must survive dust, temperature extremes, and micrometeorites. They must be designed for maintenance in bulky suits or by robots. They must fail safely in a place where cleanup is almost impossible. Again, the moon refuses to offer a clean answer. Solar power is elegant but vulnerable to darkness. Nuclear power is steady but complex. Batteries help, but add mass and aging. Fuel cells might be useful, but they require stored reactants and supply chains. Beamed power could work in some scenarios, but it adds alignment, infrastructure, and failure points. Local resource production might reduce dependence on Earth, but only after a colony already has enough energy to build the resource economy. A base can survive inconvenience. It cannot survive energy uncertainty. If power drops below a critical level, choices become brutal. Turn down heating to preserve oxygen systems. Dim the greenhouse to save communications. Shut down non-essential labs. Stop construction. Park rovers. Delay water extraction. Reduce comfort. Shorten showers if showers exist at all. Limit exercise. Put sections of the habitat into low power mode. For a visiting crew, rationing may be temporary. For a colony, rationing becomes social pressure. Who gets power for a private space? Who gets medical equipment? Who gets greenhouse light? Which experiment is cancelled? Which construction project waits? Which emergency reserve is untouchable? A technical problem slowly becomes a human problem, because a colony is not made only of machines. It is made of people living inside the consequences of machine limits. The moon's nearness does not remove that problem. Earth can send help, but not instantly. A rocket cannot be launched every time a cable overheats or a battery pack degrades. Even if rescue or supplies arrive in days, the colony must survive those days first. It must have redundancy. It must have spare parts. It must have people trained to fix systems while wearing suits that make every motion harder. This is the hidden truth behind the phrase lunar base. The base is not the building. The base is the power system that keeps the building alive. Radiation is the next problem. And it may be one of the most difficult because it is invisible. On Earth, we live beneath layers of protection. The atmosphere absorbs and scatters dangerous particles and radiation. Earth's magnetic field helps deflect charged particles from the sun and from deeper space. We do not usually feel this protection working. It is part of the background of being alive on this planet. On the moon, that background is gone. There is no thick atmosphere overhead, no global magnetic field like Earth's. A person standing on the lunar surface is much more directly exposed to galactic cosmic rays, solar energetic particles, and radiation produced when high-energy particles strike the ground and materials around them. For a short mission, radiation is a risk to manage. For a colony, it becomes a constant condition. Cosmic rays are not like sunlight that can be blocked by ordinary shade. They are high-energy particles, often moving near the speed of light arriving from outside the solar system. They can pass through materials, interact with atoms, and create secondary particles. Shielding against them is complicated because some materials can produce additional radiation when struck. More mass helps, but not always in a simple way. Solar storms are different. Most of the time, the sun looks calm from Earth, but it can release bursts of energetic particles during solar particle events. On the Moon, without rapid shelter, such events could be dangerous to astronauts working outside or living in lightly shielded structures. A colony would need radiation monitoring, storm forecasts, emergency shelters, and strict procedures. Imagine a construction crew outside the habitat. They are installing a power line between a solar array and a storage unit. The job is slow because gloves make fine work difficult. Dust clings to boots and tools. The sun hangs in a black sky. Earth is visible, but useless in the immediate moment. Then, an alert comes through the communication system. A solar event is developing. Particle levels may rise. The crew stops working. Tools are secured or abandoned. Rovers turn back. Airlocks become bottlenecks. Dust has to be controlled quickly, but not carelessly. People move toward shielded spaces. Inside the habitat, non-essential operations pause. Radiation shelter capacity matters. Timing matters. Suit condition matters. This is not drama added to make the Moon look dangerous. It is the practical reality of living without Earth's shield. A proper lunar colony would probably need buried shelters or habitats covered with regolith. Lunar soil itself could become a protective layer if piled thick enough over structures. Lava tubes, if accessible and stable, might offer natural shielding from radiation and micrometeorites. But again, protection is not free. Moving regolith requires machines. Machines require power. Excavation creates dust. Underground living complicates lighting, ventilation, emergency exits, psychological health, and construction. There is also the problem of time. Radiation exposure is cumulative. A person might accept a certain dose during a mission. A worker might accept a higher short-term risk during an emergency. But a colony implies years. It implies repeated extravehicular activities, long stays, and perhaps children. Long-term radiation risk includes cancer, damage to the central nervous system, cataracts, cardiovascular concerns, and reproductive questions that we do not fully understand in lunar conditions. A settlement cannot be designed only for healthy adults on heroic missions. If it is truly a colony, it must consider older people, sick people, pregnant people, children, and people who are not astronauts selected from a tiny elite. That changes the threshold of acceptable risk. What a trained crew accepts for 6 months may not be acceptable for a family living there for 20 years. This is where the dream becomes harder to defend. A lunar base for science and exploration is one thing. A true colony with ordinary life, generations, schools, gardens, workshops, and culture is another. The radiation environment forces a question that sounds simple but is not. How much of the Moon would humans actually get to experience? If the answer is mostly underground, behind shielding, inside sealed rooms, then colonizing the Moon may not feel like living on another world. It may feel like living inside a bunker placed beneath one. The surface would become a place for work, maintenance, science, and brief views, not casual outdoor life. No parks under open sky, no walking outside without equipment, no children running across the dust, no morning air, no rain on roofs, no unprotected window that can simply open. Radiation does not make lunar colonization impossible. It makes it less romantic. And sometimes that is more important. Then there is the dust. At first, Lunar dust sounds like a minor detail. Every world with a surface has dust. Earth has dust. Construction sites have dust. Farms, roads, basements, old books, and abandoned buildings all gather dust. It feels like an annoyance, not a civilization-level threat. But lunar dust is different. On Earth, wind and water erode particles over time. Edges are rounded. Grains are weathered. On the Moon, there is no rain, no rivers, no thick atmosphere, and no ordinary weather. The surface has been battered for billions of years by micrometeorite impacts and radiation. The result is regolith filled with fine, abrasive particles, some with sharp, glassy edges. Apollo astronauts noticed the problem immediately. Dust stuck to suits. It darkened surfaces. It got into equipment. It smelled strange when brought inside the cabin, likely because reactive surfaces met oxygen and moisture. It caused irritation. It was not just dirt from a trail. It was a persistent contaminant from a world that had never learned to be gentle. For short missions, dust was irritating. For a colony, it could become one of the main enemies. Dust can cling electrostatically. It can scratch visors. It can degrade solar panels. It can work into joints, hinges, bearings, seals, zippers, connectors, radiators, and airlock mechanisms. It can cover thermal surfaces and change how equipment absorbs or emits heat. It can be tracked inside habitats unless suits are carefully isolated from living spaces. That last point matters enormously. If astronauts wear suits outside and then bring those suits into the habitat, dust comes with them. If dust gets into the air, people may breathe it. Fine particles could irritate lungs. Sharp grains could be biologically troublesome. We do not want a lunar colony slowly turning its breathable atmosphere into a dust exposure experiment. So future habitats may need suit ports, external suit storage, dust removal systems, specialized airlocks, electrostatic cleaning methods, brushes, vacuums, sticky surfaces, filtered transition rooms, and strict procedures. A simple walk outside could become a careful contamination control operation. That is manageable for trained crews. But now imagine it as daily life. Someone repairs a rover. Someone maintains a solar array. Someone returns from a sampling trip. Someone checks a power cable. Someone works near an excavation site. Every return brings dust. Every airlock cycle is a chance for dust to enter. Every seal is a place dust can interfere. Every filter becomes a maintenance item. Every piece of clothing, every tool, every storage bin can become part of the contamination pathway. A colony does not fail only from dramatic disasters. It can be worn down. Dust is the kind of threat that attacks by accumulation. One scratch on a visor is not the end. Thousands of scratches reduce visibility. One dirty seal is fixable. Years of dirty seals increase failure rates. One dusty solar panel still works. A field of panels slowly losing efficiency becomes an energy problem. One clogged filter is replaceable. A growing pile of used filters becomes a supply chain problem. This is why dust connects to everything. It affects health, machinery, energy, thermal control, mobility, construction, maintenance time, spare parts, cleaning systems, and psychology. People living on the Moon might spend a surprising part of their lives fighting powder. And not soft powder, abrasive, clinging, ancient powder made by impacts and charged by sunlight. There is also the problem of construction. To build a protected colony, we may want to use local regolith as shielding or building material. That means digging it, moving it, processing it, sintering it, printing with it, piling it over habitats, or turning it into bricks. Every one of those activities disturbs more dust. The material we need for protection is also the material that tries to invade machines. This creates a strange loop. To survive radiation, we may need regolith. To handle temperature, we may need regolith shielding. To build landing pads and roads, we may need regolith construction. To make oxygen, we may process regolith. But the more we interact with it, the more dust becomes a daily threat. The moon offers its surface as a resource. Then, it makes that surface difficult to touch. Landing and launch create another hidden danger. On Earth, rockets launch through atmosphere, and the environment around a launch pad is designed to take punishment. Flame trenches, water deluge systems, reinforced concrete, exclusion zones, and repeated maintenance are part of the infrastructure. On the Moon, the first bases would not begin with a mature spaceport. They would begin on open regolith. Rocket exhaust in low gravity and vacuum behaves differently than it does on Earth. When a lander descends, its engines can blast lunar soil outward at high speeds. Dust and small particles can travel far because there is no thick air to slow them down. A landing near a base could sandblast equipment, coat solar panels, damage radiators, contaminate optics, and threaten habitats if infrastructure is not prepared. The same applies to launches. A vehicle lifting off from the Moon does not need as much energy as one lifting from Earth, but its exhaust still interacts with the surface. Loose regolith can be accelerated. Nearby assets must be protected. If a colony depends on regular cargo landings, then landing pads become essential, not optional. But landing pads are infrastructure. Infrastructure must be built before it can protect anything. Building it requires machines, power, materials, planning, and time. The early colony might face a chicken and egg problem. It needs deliveries to build the systems that make future deliveries safer. But early deliveries are riskier because those systems are not yet complete. This is one reason robotic preparation may matter. Before large human crews arrive, robots might need to grade surfaces, build berms, sinter regolith into hardened landing areas, place navigation beacons, install power cables, deploy communications relays, and mark safe zones. But robots on the Moon face the same dust, temperature, radiation, and power problems as everything else. If they fail, humans inherit unfinished infrastructure. A colony is not just a habitat. It is roads, pads, antennas, storage depots, emergency shelters, power stations, shielding piles, maintenance yards, rover paths, resource processing units, and safe navigation corridors. Without those, every movement becomes more dangerous. Imagine a cargo lander arriving with critical replacement parts. It has to land close enough for the crew to reach, but not so close that exhaust damages the base. If it lands too far away, unloading becomes a long rover operation. If terrain is worse than expected, cargo may be difficult to access. If the landing plume spreads dust over solar panels, the replacement parts arrive with a new problem. If the lander tips or damages itself, the colony may need to improvise. Earth's supply chains are forgiving because they are layered. A broken truck can be replaced by another truck. A damaged warehouse can be repaired with nearby crews. A delayed shipment can often be rerouted. On the Moon, every supply event is a mission. Every missed delivery has consequences. Every damaged landing site can affect the next one. The Moon's low gravity makes some things easier, but it does not remove logistics. It changes logistics into a form where everything is expensive, exposed, and hard to repair. This matters because colonization is not one arrival. It is repeated arrival. A base that receives one successful landing is impressive. A colony that receives hundreds over decades must become an operational system. It needs procedures that work when people are tired, when equipment is old, when weather on Earth delays launches, when budgets change, when emergencies overlap, and when the moon itself keeps behaving like the moon. The terrifying problem is not landing once. It is making landing routine in a place that damages routine. Micrometeorites add another quiet threat. Earth's atmosphere is a shield in ways we rarely appreciate. Small particles from space enter constantly, but most burn up before reaching the ground. We see some of them as meteors, brief streaks of light in the sky. On the moon, there is no thick atmosphere to burn them up. Small impacts can reach the surface directly. Many are tiny. Some are microscopic. But speed matters. A grain moving at cosmic velocity can carry enough energy to damage exposed equipment, pit surfaces, puncture thin materials, or slowly erode infrastructure. Over time, the colony has to be designed for an environment where little pieces of space never stop arriving. For a human, out on the surface, a suit is protection against vacuum and temperature, but it is also a fragile personal spacecraft. A puncture does not need to be large to become serious. Modern suit designs can include layers, redundancy, and damage resistance, but the risk cannot be reduced to zero. A worker far from shelter would need warning systems, repair patches, emergency oxygen, and a quick route back. For habitats, micrometeorite protection means shielding. Walls may need multiple layers. Critical modules may need to be buried or covered. Cables may need protective trenches or covers. External tanks, radiators, antennas, and solar arrays must be designed with damage tolerance. The base may need inspection robots that look for punctures, cracks, impact marks, and degraded surfaces. This adds another maintenance burden. The moon does not rust machines with rain. It does not grow vines over buildings. It does not send hurricanes. But it has its own slow violence. Radiation changes materials. Thermal cycling stresses them. Dust abrades them. Micrometeorites strike them. Vacuum outgasses them. Low gravity changes how fluids behave. There is no single enemy. There is a crowd of small ones. That is what makes long-term survival difficult. A colony must handle constant maintenance in an environment where maintenance itself is hard. To repair the outside of a habitat, people or robots must go outside. Going outside means suits, airlocks, dust control, communications, tools, oxygen, cooling, power, and risk. A task that would take 10 minutes on Earth might take hours on the moon. Gloves reduce dexterity. Shadows hide details. Tools can float or fall differently. Dust coats handles. Sharp edges matter. A dropped part may not vanish into grass, but it can still bounce, slide, or disappear into shadow. Robots can help. They may become essential. A real lunar colony would probably depend on robotic inspection, robotic construction, robotic excavation, robotic cargo handling, and robotic emergency response. But robots also break. Their joints can jam, their cameras can be blinded, their batteries can degrade, their software can misread terrain, their wheels can sink or slip, their thermal systems can fail. There is no escape from maintenance, only different layers of it. The dream of colonizing the moon sometimes imagines humans standing proudly under the black sky. But the real image may be less dramatic and more practical. People in a control room, watching dozens of maintenance feeds, checking power margins, dust levels, radiation forecasts, leak rates, battery temperatures, oxygen purity, water recovery numbers, rover telemetry, and the latest impact alerts. A lunar colony would not feel like a frontier town at first. It would feel like an operating room, a submarine, a mining site, a space station, and a disaster prevention center blended into one. Water is the promise that keeps pulling humans back to the moon. If there is usable water ice near the poles, then the moon becomes far more than a place to visit. Water can support life. It can be split into hydrogen and oxygen. Oxygen can be used for breathing or rocket oxidizer. Hydrogen and oxygen can become propellant. Water can provide radiation shielding. It can support agriculture. It can reduce the mass that must be launched from Earth. That is the dream. A lunar base near polar ice could become a refueling station, a scientific outpost, a construction site, and the first step toward a larger space economy. Instead of carrying everything from Earth, humans could begin using local resources. That idea is called in situ resource utilization, and it is one of the central arguments for returning to the moon. But the presence of water is not the same as an easy water supply. The ice is not known as a convenient underground lake with pipes waiting to be installed. Some may be mixed with regolith, some may be patchy, some may be trapped in permanently shadowed regions where temperatures are extremely low. Some may exist as molecules attached to grains or locked in forms that are difficult to extract. The exact distribution, concentration, accessibility, and mining difficulty are still major questions. A colony cannot drink headlines. It needs kilograms, tons, and then continuous production. That requires prospecting, drilling, excavating, heating material, capturing vapor, filtering contaminants, storing water, preventing losses, moving water to habitats, protecting pipes and tanks from freezing, repairing equipment in cold, dark, dusty terrain, measuring reserves accurately enough to plan growth. If the ice is rich and accessible, colonization becomes easier. If it is sparse, dirty, deeply buried, or difficult to mine, the entire economic argument changes. This is why the lunar South Pole is both exciting and dangerous. It contains some of the most valuable potential resources, but the environment is not friendly. Permanently shadowed craters preserve ice precisely because they are cold and dark. The same conditions that make them useful also make them hard to work in. A machine operating there may need its own heaters. It may need power from outside the crater. It may need communications relays because direct line of sight is blocked. It may need mobility systems that can handle slopes, rough terrain, and shadows. Now, imagine the colony depends on that machine. If the ice extractor fails, water production stops. If water production stops, the colony turns to storage. If storage runs down, every activity changes. Greenhouses may be reduced. Hygiene becomes limited. Oxygen production may be affected if water electrolysis is part of the system. Fuel production slows. Construction plans pause. Crew anxiety rises. On Earth, water systems can fail and still be supported by rivers, reservoirs, trucks, wells, rain, and regional networks. On the Moon, the water system is the environment. There is no backup lake. This does not make lunar water useless. It may be one of the most important discoveries for future exploration. But it does mean the first colony would have to treat water extraction as an industrial operation, not a simple survival trick. It would need redundancy, spare parts, trained crews, robotic support, geological mapping, storage margins, and fallback plans. A small research base can import water from Earth, if necessary. A true colony cannot depend forever on imported water. The mass and cost would be enormous. At some point, local water is either available at practical scale or the dream remains limited. The Moon may have the resource that makes colonization possible, but it hides that resource in places that colonists may struggle to reach. Food is even more complicated. In popular images, lunar colonies often have glowing greenhouses under domes, rows of plants growing beneath artificial light, and astronauts eating fresh vegetables while Earth hangs in the sky. This is not impossible. Plants can grow in controlled environments. Hydroponics and aeroponics can reduce soil needs. Closed agricultural systems could recycle water and nutrients. Fresh food would help morale and health. But farming on the moon is not farming in a field. It is life support with leaves. Plants need water, light, carbon dioxide, nutrients, temperature control, humidity control, pest control, disease monitoring, root support, and pollination strategies depending on the crop. They also need space. A colony large enough to feed itself would require substantial agricultural volume, power for lighting during darkness, systems to recover nutrients from waste, and careful biological management. The moon does not provide soil in the earthly sense. Lunar regolith contains minerals, but it is not living soil. It does not contain the rich ecology of bacteria, fungi, worms, organic matter and moisture cycles that support agriculture on Earth. Raw regolith may contain sharp particles and chemically reactive surfaces. It may require processing, washing, mixing with organic material, or replacement by hydroponic systems. So the colony's food supply begins as an engineering system. Seeds may come from Earth. Nutrients may come from Earth or from processed waste. Water must be recovered. Lighting requires power. Greenhouses must be shielded from radiation and temperature extremes. If sunlight is used, windows or mirrors must handle dust, micrometeorites, thermal stress, and radiation. If artificial light is used, power demand rises sharply. Food also introduces biological fragility. A machine can fail in predictable ways. A living system can fail strangely. Mold can spread. A crop disease can move through a greenhouse. A nutrient imbalance can reduce yields. Pollination can fail. Microbes can behave differently in low gravity. Plants may respond to partial gravity in ways that still need study over long timescales. The colony might not know which problems appear only after years. For a short mission, stored food is enough. For a colony, stored food is a countdown unless it is constantly replenished. This raises a difficult question. How self-sufficient does a lunar colony need to be before we can honestly call it a colony? If it depends on Earth for most food, most spare parts, most medicine, most electronics, and most specialized equipment, then it is more like a remote station than an independent settlement. That may be perfectly fine at first, but language matters. A base can be supplied. A colony is supposed to persist. The difference is not only population size. It is whether the settlement can survive disruptions in the connection to Earth. And the connection will be vulnerable. Launch delays happen, rockets fail, budgets shift, politics changes, supply chains break. Natural disasters on Earth can affect launch facilities. International tensions can affect cooperation. A lunar settlement that cannot survive missed shipments is not truly secure. Food is where that dependence becomes personal. People can tolerate cramped rooms for a while. They can tolerate rationed entertainment. They can even tolerate repetitive meals. But long-term nutrition, mental health, medical resilience, and social stability all depend on food being reliable. Hunger changes behavior. Shortages create conflict. Monotony wears people down. A lunar colony would need not only calories, but trust in the system that produces them. That trust is hard to build on a world that grows nothing by itself. Life support is the central nervous system of the colony. It sounds like one system, but it is really many systems working together. Oxygen supply, carbon dioxide removal, water recycling, humidity control, waste processing, air circulation, trace contaminant removal, temperature regulation, fire detection, pressure control, microbial monitoring, food production if the colony becomes more closed. On Earth, these tasks are distributed through nature and infrastructure. Plants, oceans, rivers, Weather, bacteria, soil, and atmosphere all participate in keeping the planet habitable. Human technology modifies that environment, but does not create the entire thing from scratch. On the Moon, the habitat has to imitate the most important parts of Earth inside a sealed machine. That is harder than it sounds. A closed life support loop is never perfectly closed. Filters need replacement. Chemicals are consumed. Parts wear out. Microbes grow where they should not. Sensors drift. Pipes accumulate deposits. Pumps fail. Valves stick. Water quality changes. Air composition must be monitored constantly. Waste has to be processed safely. Every leak is a loss. Every contaminant has fewer places to go. The International Space Station has taught humans a great deal about recycling water and managing air in orbit. But the station is close to Earth, regularly resupplied, continuously monitored, and occupied by small crews. A lunar colony would push the problem further. More people, more time, more dust, more partial gravity, more industrial activity, more reliance on local resources, more expectation of growth. Growth is dangerous because it changes loads. A life support system designed for 6 people cannot simply support 60 without major expansion. More people produce more carbon dioxide, more wastewater, more heat, more trash, more microbial load, more medical needs, more food demand, and more opportunities for error. Every new module has to connect safely to the larger system. Every expansion is a new failure path. A colony may therefore grow slowly, not because of ambition, but because life support does not like sudden ambition. There is also fire. On Earth, fire is dangerous. In a sealed lunar habitat, it can be catastrophic. Flames behave differently depending on airflow and gravity. Smoke has nowhere harmless to disperse. Toxic products can contaminate the atmosphere. Fire suppression must not poison the crew or destroy essential systems. Oxygen levels must be managed carefully. Materials must be chosen to resist ignition. A small electrical fire inside a lunar habitat would be a nightmare. Not because it would necessarily burn the entire base, but because response options are limited. You cannot open windows. You cannot simply evacuate outdoors without suits and airlock procedures. You cannot allow smoke to spread through the only breathable air. You must isolate, suppress, ventilate, filter, inspect, repair, and restore trust in the system. This is why a lunar colony would be designed around compartments. The ability to seal off a damaged section may save the rest. But compartmentalization also affects daily life. Doors, hatches, emergency routes, redundant oxygen lines, backup power, and independent shelters become part of architecture. People may live in a place where every room has a role in disaster survival. That changes psychology. A house on Earth can be cozy because the outside world remains broadly survivable. A lunar habitat can be comfortable, even beautiful, but beneath the comfort is always procedure. There is always training. There are alarms, there are drills, there are checklists, there are emergency masks, suits, repair kits, pressure doors, backup tanks, and shelter maps. The colony is alive only because it keeps checking itself, and if that checking ever stops, the Moon does not help. Communication with Earth is both reassuring and painful. The Moon is close enough that conversations are almost real-time. Radio signals take about 1¼ seconds to cross the average Earth-Moon distance. One way, so a voice delay exists but does not destroy communication. Compared with Mars, where delays can stretch to many minutes, the Moon feels connected. That connection matters. Doctors on Earth can consult. Engineers can advise. Families can call. Mission Control can monitor systems. Scientific teams can help plan work. In an emergency, people on Earth can understand what is happening quickly. But communication is not rescue. Advice can cross space in seconds. Hardware cannot. If a pump fails, Earth can send instructions, but the crew must repair it. If a rover breaks down beyond walking range, Earth can help diagnose the issue, but someone on the Moon has to solve the immediate problem. If a radiation storm forces people into shelter, Earth can track the event, but Earth cannot stand between the particles and the habitat. The Moon is close enough to make help feel present, but far enough that the colony remains physically alone. This produces a strange emotional condition. Earth is visible. Earth is reachable by radio. Earth is the origin of supplies, families, culture, weather, oceans, forests, and every human memory before the colony. Yet outside the habitat, Earth might as well be another universe. You can look at it through a window while knowing you cannot breathe the space between. That may be psychologically harder than deeper isolation. On a Mars mission, Earth becomes a bright point in the sky. On the Moon, Earth is a world-sized reminder. It hangs there, detailed enough to recognize too far to touch. A colonist could watch storms moving across Earth while standing in a place with no rain. They could see blue oceans while rationing water. They could see clouds while living under a sky that never changes. The Moon's silence would also shape the mind. No breeze crosses the lunar ground, no animal life, no leaves, no insects, no natural water sounds, no open air. The only sounds are human-made: fans, pumps, voices, footsteps, alarms, tools, radio static, machinery, and the interior hum of survival. Outside, sound cannot travel through vacuum. A massive object could fall in the distance and produce no sound through the air, because there is no air. For some people, that silence might feel peaceful. For others, it could become oppressive. A real colony would need mental health systems as seriously as oxygen systems. Private space, social routines, windows if radiation shielding permits them, artificial day-night cycles, communication with Earth, meaningful work, recreation, conflict resolution, medical support, rituals, art, music, shared meals, reasons to continue beyond simply not dying. This is where the word colonization can become misleading. People do not settle a place only with machines. They settle it with habits. A lunar colony would need to invent habits for a world with no sunrise in the ordinary sense, no weather, no outdoor life, no open horizon without a suit, and no biological environment beyond what humans bring. It would need culture, not just infrastructure. The first crews might be motivated by exploration, the next groups might be motivated by science, engineering, national prestige, or private opportunity. But a permanent population needs a deeper reason to accept the trade. What does a person gain by living there? Scientific purpose? Economic opportunity? A new society? A role in human survival? The experience of seeing Earth from outside? The chance to build something never built before? Those reasons may be powerful. But the Moon will ask for payment every day. Low gravity is another problem hidden behind the excitement. The Moon's gravity is about 1/6 of Earth's. That makes movement strange and almost playful in short videos. Astronauts bounce. Dust arcs differently. Heavy objects weigh less. A person can carry more mass than they could on Earth, at least in terms of weight. Launching from the surface is easier. Construction equipment might handle loads differently. At first, low gravity sounds like an advantage. For machines, it can be. For rockets, it definitely is. For human bodies, the answer is less clear. We know that microgravity in orbit harms the body over time. Astronauts can lose bone density and muscle mass. Fluids shift, balance changes. The cardiovascular system adapts. Exercise helps, but it does not perfectly replace gravity. The Moon is not microgravity, so it may be better than orbit. But we do not know whether 1/6 gravity is enough for long-term health over years, pregnancies, childhood development, aging, and recovery from injury. That uncertainty matters. A base for short stays can manage with countermeasures. A colony requires confidence that people can live entire lives. If lunar gravity is too weak to maintain bones, muscles, circulation, or normal development, then colonization becomes far more complicated. Artificial gravity could help, but it is difficult. A rotating habitat could create centrifugal acceleration, but building large rotating structures on or near the Moon adds complexity. People might spend part of each day in a centrifuge for health. But how large should it be? How fast should it rotate? How much time is enough? How would it affect children? What medical issues appear after decades? These are not minor details. A colony is not successful if its people slowly become unable to return to Earth, unable to stay healthy, or dependent on constant medical intervention. Some science fiction embraces that idea, imagining lunar-born humans adapted to low gravity. But biological adaptation is not a plan. It is a gamble across generations. Low gravity also affects practical systems. Dust falls differently. Fluids behave differently than on Earth. Cooking changes, showers, toilets, medical procedures, agriculture, manufacturing, and construction may all need redesign. A person injured in low gravity may move differently, bleed differently in some situations, or require different handling. Fire, behavior, airflow, and particle movement can change in ways that must be tested carefully. The Moon may be close to Earth, but its gravity is not a smaller version of Earth life. It is a new regime. This is one reason a lunar colony would be an experiment, even after it is built. Every year of habitation would answer questions we cannot fully answer from Earth. How do children grow in 1/6 gravity? Can pregnancy proceed normally? How do immune systems respond? Do bones stabilize at a lower density or keep weakening? How does the brain adapt to lifelong partial gravity? What happens after decades? Until those answers exist, permanent settlement carries biological uncertainty. And uncertainty is hard to sell as home. And that is before the colony has to become more than a laboratory. A base can survive with procedures, checklists, replacement parts, and a crew rotation schedule. A colony needs something deeper. It needs ordinary life to continue inside an environment that never becomes ordinary. People have to wake up, work, argue, recover, make decisions, raise children, repair walls, bury the dead, and keep the lights on when Earth is only a bright object in the black sky. That is where the Moon becomes more disturbing than it first appears. The hard part is not only building pressurized rooms. The hard part is building a world that can keep functioning after the first heroic mission is over. A colony cannot depend on perfect astronauts forever. It has to handle tired people, old people, injured people, frightened people, and children who never chose the risk. On Earth, civilization is protected by layers most people never notice. There is an atmosphere above us, a magnetic field around us, oceans that store heat, soil full of microbes, clouds that carry water, hospitals, roads, farms, supply chains, emergency services, and millions of strangers doing invisible work. On the Moon, almost all of that has to be manufactured. A broken pipe is not just plumbing. It may be part of the water loop. A stuck valve is not just a maintenance issue. It may control oxygen, coolant, waste processing, or pressure balance. A cracked window is not a window problem. It is a vacuum problem. A kitchen fire is not a kitchen fire. It is a closed atmosphere emergency inside a habitat surrounded by an airless world. That is the real difference between visiting the Moon and living there. Visiting means bringing what you need, staying alert, and leaving before the environment wins. Living means asking the environment to stop winning every day. The first colonies would likely be planned around redundancy. 2 power systems instead of 1. Multiple air loops. Several water tanks. Backup communications. Separated sleeping quarters. Fire doors. Emergency shelters. Medical isolation rooms. Spare suits. Spare suit parts. Spare parts for the spare parts. A settlement that depends on a single perfect chain is not a settlement, it is a countdown. But redundancy creates weight, cost, and complexity. Every extra component must be launched, landed, tested, stored, tracked, and maintained. If it comes from Earth, it is expensive. If it is made on the Moon, the factory that makes it needs power, tools, raw material, people, and repair equipment of its own. The support systems begin to support systems, and the colony becomes a machine trying to keep another machine alive. This is why the Moon is terrifying as a home. Not because every danger is mysterious, but because many dangers are ordinary on Earth and catastrophic there. Imagine a simple medical emergency. A person slips while carrying equipment across a dusty corridor, hits a metal frame, and breaks a leg. On Earth, that is painful, but the system around the injury is familiar. Ambulance, hospital, surgeon, imaging, blood supply, sterile rooms, medication, rehabilitation. On the Moon, the same injury becomes a logistics problem. How do you move an incapacitated person through narrow hatches? Can a suit fit over a splint? What if the accident happens outside? What if the airlock is contaminated with dust and the injured person is losing oxygen? What if a doctor is not present, or the doctor is the injured person? A serious colony would need medical autonomy. It would need imaging equipment, surgical tools, pharmaceuticals, sterilization, blood substitutes, or stored blood products, dental care, mental health support, rehabilitation devices, and trained personnel who can handle trauma without help arriving quickly. A delay of seconds matters in an emergency. Earth is close compared with Mars, but it is not close enough to send a surgeon through a radio call. Remote guidance can help. A specialist on Earth can advise the crew with only a small delay. But advice is not hands. Instructions do not stop bleeding by themselves. Robotic surgery may become useful, but robots also fail, need calibration, and require trained operators. The more capable the system becomes, the more systems must exist to keep it capable. Now, imagine pregnancy. It sounds like a distant question, but a true colony eventually has to face it. If no children can be born safely on the Moon, then the colony is not a self-sustaining branch of civilization. It is an outpost with a population constantly replaced from Earth. That may still be valuable. It may support science, mining, astronomy, and exploration. But it is not the same as humanity becoming lunar. Pregnancy in 1/6 gravity is not a solved problem. Fetal development evolved under Earth gravity. The skeleton, muscles, vestibular system, cardiovascular system, and immune system all develop through signals we do not fully understand. Birth itself involves mechanics. Infant development involves movement, balance, crawling, standing, falling, and recovering. A lunar-born child might grow normally, or might not. The answer cannot be guessed with confidence from short missions in orbit. Ethically, that is enormous. A colony can accept risk for consenting adults. It becomes much more complicated when the risk is placed on children. Who decides that a child should be born in low gravity before medicine knows the consequences? What happens if a lunar-born body cannot safely return to Earth? Would those children become physically tied to the Moon? Would visiting Earth be painful, dangerous, or impossible? A dream of settlement can quickly become a question of rights. The Moon is not only a physics problem, it is a human society problem. Even if reproduction is delayed, mental health becomes unavoidable. The first colonists would live in a place with no weather, no forests, no rivers, no open air, and no natural soundscape. They would see the same grey terrain every time they looked outside. Above it would be blackness in the middle of the day because the moon has no atmosphere to scatter sunlight into a blue sky. The sun would be harsh and white. Shadows would be sharp. The horizon would be close. Earth would hang in the sky from many locations on the near side, large enough to be seen clearly, but impossibly unreachable in an emotional sense. It would show oceans, storms, continents, and the entire living world. That view may inspire people for a while. It may also make the habitat feel smaller. The more beautiful Earth looks, the more obvious the difference becomes. A person on the moon cannot step outside for air. There is no walk to clear the mind unless the suit is checked, the airlock is cycled, the route is planned, and someone monitors the excursion. There is no rain on a roof. There are no birds at dawn. There is no wind through trees. There may be recorded sounds, plants in controlled rooms, artificial sunlight, exercise spaces, virtual environments, and communal rituals. But all of them are substitutes. Useful substitutes, perhaps beautiful ones, but substitutes. That matters because colonies fail socially before they fail mechanically if people stop believing the place is livable. A lunar settlement would need more than engineering. It would need culture. It would need schedules that prevent burnout. Private spaces that actually feel private. Communal rooms that do not feel like machinery. Meaningful work, education, art, rituals, and ways to handle conflict. If every argument happens inside a sealed habitat where nobody can leave, small social problems become environmental problems. Every community has disagreements. On Earth, distance softens them. People go home, take a drive, visit friends, change cities, or spend time outside. On the moon, the community is the life support system. Your enemy may also be the person who repairs the oxygen processor. Your divorce may happen in the same module where you both have to work tomorrow. Your political dispute may involve water allocation, power use, or whether a risky repair should be attempted before Earth resupply. Law becomes physical. A rule about opening an airlock is not just policy. A rule about dust control is not just cleanliness. A rule about quarantine could save the entire food system. Punishment, privacy, leadership, consent, ownership, labor rights, emergency authority, and resource rationing all become more urgent because the environment leaves less room for mistakes. The moon would also force humanity to answer an old question in a new place. Who owns what? The Outer Space Treaty says outer space, including the moon, is not subject to national appropriation by claims of sovereignty. But a working colony still needs rules about mining sites, landing zones, roads, power stations, habitats, buried cables, and protected scientific areas. If one group builds a solar farm on a ridge of near-continuous sunlight, can another group land nearby and throw dust over it? If one company extracts water ice from a permanently shadowed crater, how much is too much? If a historic Apollo site is damaged by a private lander, who is responsible? A colony lives inside law as much as inside metal, and law becomes harder when every useful location is rare. The lunar South Pole is attractive because certain high regions may receive long periods of sunlight, while nearby permanently shadowed craters may preserve water ice. That combination sounds perfect. Power nearby, water nearby, science nearby. But the word nearby is doing a lot of work. The terrain can be rugged, shadows can be extremely cold, communication can be blocked by local topography. Driving from a sunlit ridge to a dark crater may be slow, dangerous, and energy-intensive. A map makes it look simple. The ground will not. Permanently shadowed regions are some of the coldest environments in the solar system. Equipment that enters them must survive temperatures that can make materials brittle and electronics unhappy. Solar power is unavailable inside the shadow itself. Excavation becomes harder when machinery is operating in darkness, cold, dust, and uneven terrain. If water ice is mixed with regolith, it has to be dug, transported, heated, captured, filtered, stored, and protected from contamination. Water is not useful until it is in a tank where humans can use it. The same water may have several jobs. It can be drinking water. It can be split into hydrogen and oxygen. Oxygen can support breathing or rocket oxidizer. Hydrogen can become fuel if handled correctly. Water can shield against radiation. It can support plants. It can help regulate temperature. That makes it valuable. But value creates pressure. The colony may begin as science and quickly become extraction. Extraction creates its own problems. Digging changes the terrain. Heating regolith releases gases and dust. Machinery wears down. Ice deposits may be patchy. A site that looks promising from orbit may disappoint on the ground. If a colony is designed around local water, and the water is harder to access than expected, the settlement becomes dependent on imports again. If the water is abundant but expensive to mine, the colony survives only if someone pays the cost. This is why water ice is not a magic solution. It is a possibility that still has to be engineered into reliability. The same applies to oxygen from lunar soil. Lunar regolith contains oxygen bound inside minerals. In principle, processing regolith can release oxygen, and that could support breathing or propellant production. But extracting oxygen from rock is industrial work. It requires heat, reactors, feedstock handling, storage tanks, maintenance, and a large amount of energy. On Earth, industrial plants sit inside a world that already has air, water, cranes, roads, workers, warehouses, spare parts, and emergency crews. On the Moon, the plant has to bring its own civilization with it. A lunar colony may eventually make bricks, metals, glass, oxygen, landing pads, and structural components from local material. That would reduce reliance on Earth. But the path from experiment to dependable industry is long. A machine that works for a week during a technology demonstration is not the same as a machine that runs for 10 years in dust, radiation, thermal cycling, and low gravity. Industry also needs waste handling. Every settlement creates waste: broken parts, worn filters, contaminated dust, packaging, human waste, failed crops, damaged electronics, medical waste, and chemical byproducts. On Earth, waste disappears from most people's view because a massive system moves it elsewhere. On the Moon, elsewhere is still part of the base. Dumping material outside may be easy at first, but it can create contamination, dust hazards, navigation hazards, and future cleanup problems. A true colony has to become circular. Water is reclaimed, air is scrubbed, nutrients are recovered, organic waste becomes fertilizer. After careful processing, metals are reused, plastics are recycled or remade, broken electronics are cannibalized, packaging is minimized. Nothing can be treated as disposable in the Earth sense, because disposal means turning imported mass into useless mass. But closed loops are difficult. The International Space Station recycles much of its water, but it is resupplied from Earth and maintained by a massive ground support network. A moon colony would need more independence. It would need systems that tolerate dirty inputs, unexpected failures, microbial growth, chemical buildup, and human error. A filter that clogs too often can become a life-threatening bottleneck. A water recycler that depends on a single imported membrane can become a hidden weakness. Food may be even harder. The first lunar residents would probably eat packaged food from Earth, supplemented by experimental crops. Packaged food is safe, predictable, and relatively simple. It is also not a long-term civilization. A real colony needs fresh food, calories, nutrients, psychological comfort, and agricultural resilience. Plants can help recycle carbon dioxide into oxygen. They can support morale. They can make sealed rooms feel alive. But farming on the moon is not simply planting seeds in lunar dirt. Lunar regolith is not soil. It lacks the organic structure, microbial ecosystem, moisture retention, and nutrient cycling that Earth soil has. It can contain sharp particles and reactive surfaces that are not friendly to roots or lungs. Growing plants would likely require hydroponics, aeroponics, processed regolith, imported nutrients, carefully controlled lighting, water recycling, and pest management inside sealed environments. A greenhouse on the moon is not a garden under glass. It is a spacecraft that happens to grow lettuce. Lighting matters. If plants rely on sunlight, the long lunar day-night cycle becomes a challenge. If plants rely on LEDs, the power demand grows. Temperature control matters. Humidity control matters. Pollination may require manual work or small robotic systems. Diseases can spread quickly in closed plant habitats. A failed crop is not just disappointing. It can change food reserves, oxygen balance, crew morale, and mission planning. The food system becomes another machine that must stay alive. Then comes fire. Fire is one of the most frightening emergencies in any sealed habitat. On Earth, smoke can spread, but buildings usually have exits into breathable air. On the moon, the outside is vacuum. You cannot simply run outside and wait for firefighters. The habitat, atmosphere, pressure, airflow, materials, alarms, extinguishers, and emergency shelters all have to be designed around the fact that the emergency is trapped with you. A lunar fire may start small. Overheated electronics, a short circuit, a battery failure, a cooking accident, a chemical reaction, dust inside equipment, or a damaged cable. In a closed system, smoke contaminates the air. Toxic gases spread through ventilation. Fire consumes oxygen. Heat damages seals. Panic causes mistakes. If power is cut to isolate the fire, other systems may shut down too. The solution is compartmentalization. Habitats need sections that can be sealed quickly. Airflow must be controlled. Materials must be fire-resistant. Cables must be protected from abrasion and dust. Batteries must be monitored. Emergency masks, portable oxygen, and safe rooms must be available. People must drill until the procedure is automatic. A colony that treats fire as unlikely is not serious. The problem is that safety design can make daily life more difficult. More doors mean more bottlenecks. More seals mean more maintenance. More compartments mean more complex movement. More emergency rules mean more training. A lunar settlement must balance comfort against survival, and survival will often win. Another hidden enemy is pressure cycling. Every time an airlock opens and closes, mechanical parts move, seals flex, dust tries to enter, and gas is lost or recovered. Every suit port, rover hatch, cargo lock, and maintenance access point is a place where the inside world meets the outside world. A tiny leak can become routine if detected early. An undetected leak can become a disaster. Leaks do not have to be dramatic. They can begin as a slow pressure loss that forces the system to work harder. They can hide behind panels. They can appear after thermal expansion and contraction. They can be caused by dust on a seal, a micrometeoroid puncture, a manufacturing flaw, or a human mistake during maintenance. The colony must constantly listen to itself, measuring pressure, flow, humidity, gas composition, and structural strain. Living on the moon means living inside instrumentation. A person may not feel danger until a display shows it. The habitat can look calm while a hidden sensor reports trouble. This changes the psychology of home. On Earth, people trust the air because it has always been there. On the moon, air is a number. Water is a number. Radiation is a number. Carbon dioxide is a number. Every comfort becomes a monitored variable. That constant monitoring can save lives, but it also reminds everyone that the home is artificial. Outside, micrometeorites keep arriving. The moon has no thick atmosphere to burn up incoming grains of cosmic debris. Tiny particles can strike at high speeds. Many are harmless against proper shielding, but a colony has a much larger surface area than a small spacecraft. Solar arrays, radiators, tanks, cables, antennas, greenhouse panels, rovers, storage containers, and exposed equipment all become targets. Shielding habitats is possible. Regolith can be piled over structures. Whipple shields can break up small impactors. Critical modules can be buried or placed inside natural terrain. But exposed infrastructure remains vulnerable. A punctured radiator may reduce heat control. A damaged power cable may cut electricity to an isolated unit. A cracked greenhouse panel may destroy months of plant growth. A hit on a tank can turn stored resources into lost resources. The most dangerous impacts may not be the largest. A large impact is obvious and rare. Small damage can be quiet, cumulative, and expensive. It creates maintenance work, replacement demand, and constant inspection. A colony cannot simply be built and left alone. It must be patrolled like a ship at sea. That comparison is useful, but incomplete. A ship at sea floats in an environment that can also kill you, but the ocean is at least part of Earth's biosphere. A lunar colony is more like a submarine that cannot surface, a mining town that cannot breathe outside, and a spacecraft that is expected to become a city. This makes rescue a central problem. The moon is close enough that rescue seems possible. That can be misleading. A spacecraft cannot launch instantly like a helicopter. It must be available, fueled, checked, and aligned with orbital mechanics. Weather on Earth can delay launch. Technical issues can delay launch. A landing site may be unsafe. A rescue crew may not know the exact condition of the damaged habitat. If the emergency is oxygen loss, fire, radiation exposure, medical trauma, or power collapse, the time window may be measured in hours. A colony that depends on rescue is not a colony. It is a remote camp with a very expensive ambulance. Real safety would come from internal rescue, safe rooms with independent life support, pressurized rovers that can act as temporary shelters, multiple habitats separated by enough distance that one disaster does not destroy all of them, but close enough that crews can move between them. Spare suits in different modules, emergency tunnels or covered paths, communication systems that still work when the main network fails. Even evacuation is complicated. Where does everyone go? A small outpost can plan for a full evacuation back to Earth. A large colony cannot assume that every resident can leave quickly. Launch vehicles have limited seats. Propellant must be stored. Landing and launch pads must survive repeated use. If the colony grows into hundreds or thousands of people, Earth return becomes a selective option, not a universal one. That changes the meaning of risk. For the first crews, the moon is a mission. For later residents, it may become a place they cannot easily leave. Economic status, health, job role, citizenship, company rules, launch schedules, and family ties could determine who gets to go home. A failure in colony planning could become a human rights problem. The moon forces space settlement to become political before it becomes romantic. Now, consider the outside economy. Why colonize the moon at all? Science is a strong reason for bases. The moon preserves records of solar system history. Its far side could support radio astronomy shielded from Earth's radio noise. Its surface can test technologies for Mars and deep space. Its polar water may support fuel production. Its low gravity may make some launches easier than from Earth. It may support tourism, research, manufacturing, and training. But science bases and colonies are not the same thing. A science base can be justified by knowledge. A colony needs a durable reason to grow. If everything the colony uses is imported from Earth, it remains expensive. If exports are weak, funding depends on politics, prestige, or strategic competition. If mining is the reason, the material must be worth the cost of extracting and moving it. If fuel is the reason, there must be customers. If tourism is the reason, safety and comfort must improve dramatically. A settlement becomes stable when it has work that pays for its own survival. That may happen, but it is not automatic. The moon is not full of easy treasure waiting to be scooped up. It has useful materials, but useful does not mean profitable. Oxygen in rock is useful. Water ice is useful. Metals are useful. Regolith is useful for shielding and construction. But every process must compete with launching material from Earth or producing it elsewhere. Economics may be one of the most terrifying problems because it is less cinematic than radiation, but just as deadly. A base can be abandoned if funding dries up. A half-built colony can become a monument to optimism. People imagine explosions ending lunar dreams, but budgets can do it quietly. A colony also has to survive success. If it grows, it needs more power, more water, more waste processing, more landing capacity, more governance, more healthcare, more food production, more living space, and more conflict resolution. Growth creates traffic. Traffic throws dust. Dust damages equipment. More people generate more heat. More heat requires larger radiators. Larger radiators need more area and protection. More industrial activity increases accident risk. The first small habitat is difficult, but scaling it into a town may be harder. Every new module changes the system. A module must be connected, pressurized, powered, monitored, and integrated into life support. A new crew changes resource demand. A new greenhouse changes humidity, insects or microbes, lighting and nutrient flow. A new factory changes dust, heat, power use, and waste. The settlement becomes less like a spacecraft and more like an organism with many organs. Organisms can get sick. A software error can shut down equipment. A bad batch of filters can weaken air quality. A design flaw can appear only after years of thermal cycling. A contaminated water tank can spread illness. A power surge can damage multiple systems. A dust storm cannot happen in the lunar vacuum, but a dust accident created by human activity can still blanket equipment. A landing plume can sandblast nearby surfaces if landing pads are inadequate. This is why infrastructure comes before comfort. Landing pads sound boring until a rocket engine throws abrasive regolith across a base. Roads sound boring until rovers keep sinking, slipping, or grinding dust into moving parts. Power cables sound boring until darkness cuts a habitat from the grid. Storage depots sound boring until a delayed launch leaves the colony short of critical parts. A mature moon settlement would need pads, berms, roads, buried cables, navigation beacons, dust control zones, repair shops, warehouses, shelters, radiation bunkers, and clear traffic rules. It would need the unglamorous anatomy of a town. The danger is that people often imagine the habitat first and the infrastructure later. On the moon, That order may be backwards. The surface is not forgiving enough for improvisation at scale. Before large numbers of people arrive, robots may need to prepare sites, clear paths, build landing areas, bury power lines, test resource extraction, map ice, deploy communication relays, and assemble shielding. Humans may then move into a landscape already partially shaped for survival. That is, less dramatic than planting a flag, but more important. The best lunar colony may not look like a row of glass domes. Glass domes are beautiful in art and terrible in engineering. They expose people to radiation, micrometeorites, heat loss, pressure loads, and dust. They require large, transparent materials that must hold atmosphere while facing an environment that wants to break them. Real habitats may be squat, covered, partly buried, windowless, and practical. The first true lunar city might be invisible from a distance. It may sit beneath regolith, inside covered trenches, or within lava tubes if safe and accessible ones are found. Its beauty would be internal: warm rooms, controlled light, plant walls, clean air, soft surfaces, quiet sleeping spaces, workshops, medical bays, and observatories pointed at the universe. The outside would remain lethal, but the inside could become human. Underground living solves some problems and creates others. Regolith shielding can reduce radiation and protect against small impacts. It can smooth temperature swings. It can make habitats safer. But burying structures complicates access, inspection, repair, expansion, and emergency escape. A lava tube could offer natural protection, but it must be mapped, stabilized, sealed, lit, supplied with air, and connected to the surface. If a collapse happens, rescue becomes difficult. If access shafts fail, the protected shelter becomes a trap. There is no free safety. Every solution on the moon has a cost, and the costs interact. More shielding means more mass or more excavation. More excavation means more dust and machinery. More machinery means more power and maintenance. More power means more infrastructure. More infrastructure means more surfaces that can break. More people mean more capacity, but also more consumption. Less dependence on Earth means more local industry, and local industry adds complexity before it adds freedom. A lunar colony is not one problem. It is a knot of problems. The terrifying part is that each individual problem can be solved in principle. We can build pressure vessels. We can recycle water. We can shield against radiation. We can grow food in controlled systems. We can generate power. We can map ice. We can send robots. We can train crews. We can design emergency protocols. None of the pieces are magic. But a colony is what happens when all pieces must work together for years, then decades, then generations. That is where confidence becomes more fragile. A mission can accept a high maintenance burden because it ends. A colony cannot treat constant emergency repair as normal life forever. A base can ration comfort because the crew goes home. A colony has to provide a reason to stay. A research station can depend on Earth because its purpose is limited. A civilization branch has to grow beyond dependency. The moon tests whether human technology can become ecology. On Earth, ecosystems are not designed by one agency. They are vast, messy, redundant, self-adjusting webs built over billions of years. A lunar colony would need an artificial ecology built intentionally. Air, water, food, waste, microbes, machines, people, energy, law, and culture bound together. If one part fails, the others must absorb the shock. That is a much harder task than landing. Landing is a moment. Settlement is a continuous negotiation with physics. To understand how fragile that negotiation could be, imagine a realistic failure chain. A cargo lander arrives slightly off course and touches down closer to the base than planned. Its engine plume throws dust farther than expected. Some particles strike radiator surfaces and solar panels. Power output drops by a few percent. At first, the colony handles it. Batteries cover the difference. Crews schedule cleaning. Then, a dust-coated radiator becomes less efficient during a warm period. A coolant pump runs harder. A bearing, already worn by months of vibration, begins to fail. The maintenance team diverts time to the pump. While they work, a greenhouse lighting cycle is reduced to save energy. The plants survive, but growth slows. Food reserves are still fine, but morale dips because fresh food becomes less frequent. A spare part for the pump was supposed to arrive on the next cargo flight. That flight is delayed by a launch issue on Earth. The colony is not in immediate danger, but several margins are now thinner. Then, a small leak appears in a storage module seal contaminated by dust from repeated suit operations. The leak is found, but repairing it requires cycling an airlock more often than planned. Gas losses increase. The oxygen plant must run longer. The oxygen plant uses power. Power is already tight. None of these failures alone would destroy a base. Together, they create stress. People sleep less. A technician makes a mistake. A scheduled inspection is postponed. A minor problem waits one day too long. This is how real disasters often grow. Not from one cinematic event, but from small losses of margin. A good colony design fights margin loss. It assumes dust will spread, pumps will fail, people will get tired, flights will be delayed, sensors will lie, and parts will wear out early. It keeps reserves not because planners are pessimistic, but because the moon punishes optimism that has no backup. That may sound cold, but it is the language of survival. The first permanent lunar settlement would probably be less like a dream city and more like an Antarctic station. Submarine, oil platform, mining operation, nuclear plant, hospital, farm, and spacecraft combined. Every resident would live inside overlapping procedures. Every casual routine would have emergency meaning. Every beautiful moment would be surrounded by equipment. And there would be beautiful moments. The point is not that the moon is only horror. A person standing safely inside a lunar habitat could look through a protected viewing port and see Earth hanging over a grey horizon. They could watch sunlight crawl across crater rims. They could see stars without atmospheric shimmer. They could walk in low gravity and feel the body move in a way no human evolved to feel. They could help build the first off-world settlement in history. That is powerful. But beauty does not remove danger. It makes the danger worth understanding honestly. A truthful moon colony story is not about humans easily conquering a nearby rock. It is about humans building a fragile pocket of Earth on a world that has never needed life. It is about making air where there is none, holding warmth where heat escapes or floods in, keeping water from disappearing into vacuum, and protecting bodies from radiation they cannot feel until damage is done. It is about turning a place of footprints into a place of routines. The Apollo astronauts visited the moon with extraordinary courage, but they did not have to make it normal. Future settlers would have to do exactly that. They would have to make the impossible boring enough to repeat. Boring air checks, boring dust inspections, boring water accounting, boring radiation shelter drills, boring exercise schedules, boring agricultural logs, boring maintenance reports. That boredom would be victory. A colony becomes real when survival stops being heroic and starts being reliable. But reliability on the moon will never mean the environment becomes friendly. It will mean the systems are strong enough that people can live with the hostility without thinking about it every second. That is how humans have always expanded into difficult places. We do not make the ocean breathable. We build ships. We do not make Antarctica warm. We build stations. We do not make orbit safe. We build spacecraft. The moon would be the next version of that pattern, but harsher because the outside offers no biological forgiveness. There is also the problem of time. The moon is close enough that a message reaches Earth quickly, but close communication does not mean shared life. A base can ask for advice. A colony has to make decisions. If a pump fails at 3 in the morning lunar time, the person in charge cannot wait for a committee on Earth to wake up. If a child becomes sick, if a rover is trapped, if a solar storm warning arrives, or if two groups disagree over who gets emergency power, authority has to exist locally. That sounds obvious until the colony is funded, supplied, insured, and politically controlled by organizations on Earth. Who commands during a crisis? The mission director? The local commander? The elected council of residents? The company that owns the habitat? The country that launched the power system? A legal document written on Earth can look clean until people are suffocating inside a module, and two procedures disagree. A colony cannot be governed like a remote machine forever. The more people live there, the more the moon becomes a community rather than equipment. Communities need legitimacy. They need trust in leadership. They need rules that residents believe are fair. They need ways to challenge decisions without endangering operations. They need emergency authority that is strong enough to act quickly, but limited enough not to become permanent control. That may sound political, but on the moon, politics is life support. A dispute over mining location can affect water. A dispute over energy use can affect heating. A dispute over who works outside can affect radiation exposure. A dispute over launch seats can affect who survives an evacuation. Earth has the luxury of separating many arguments from basic survival. The moon ties them together. Then there is communication with the rest of humanity. The near side of the moon can see Earth, but not every location has a perfect direct line all the time. Terrain can block signals. Equipment can fail. Solar storms can interfere. The far side needs relay satellites. A serious lunar civilization would require a communication network as reliable as its power grid. Navigation beacons, emergency channels, data links, medical lines, scientific transmissions, and personal communication would all depend on infrastructure around a world with no towers, no atmosphere, and no repair truck waiting down the road. That network would carry more than instructions. It would carry family calls, education, entertainment, news, arguments, therapy, engineering updates, and the emotional connection to Earth. If communication fails for an hour, it may be annoying. If it fails during a medical emergency, it may be fatal. If it fails during a political crisis, rumors can grow inside a sealed community very quickly. Isolation is not only physical, it is informational. A colony cut off from Earth, even temporarily, becomes its own small universe. People inside may still have food, power, and air, but uncertainty can spread faster than a leak. What happened? Is Earth responding? Is the fault local? Is more equipment failing? Should crews stay inside? Should they prepare evacuation? A good communication system prevents technical silence from becoming social panic. Software becomes another hidden frontier. Modern spacecraft are filled with code. A lunar colony would be even more dependent on automated monitoring, robotic inspection, inventory systems, agricultural controls, navigation, power management, thermoregulation, air recycling, water processing, and medical diagnostics. A software bug could misread a sensor. A faulty update could shut down an important process. A cyber attack, even if unlikely in the early years, becomes a real concern once commercial and national interests grow. On Earth, a bad software update can stop banks, airports, or hospitals. On the Moon, a bad update could affect breathing, That means the colony needs digital resilience. Offline modes, manual overrides, verified updates, isolated safety systems, crew training for degraded operations. Hardware that can operate without constant connection to Earth. Engineers who can read logs, replace boards, patch software, and understand old systems after the original designers have moved on. The danger is not that artificial intelligence becomes evil. The practical danger is more boring. Automation becomes trusted beyond what it deserves. If the colony grows comfortable, letting software balance oxygen, schedule maintenance, assign rover routes, control crop lighting, and manage power loads, people may slowly lose the ability to operate without it. Then, a fault that would have been manageable becomes confusing because no one remembers the manual procedure well enough. Over-automation can turn expertise into dependence. A lunar settlement has to keep human skill alive. That means drills, apprenticeships, written manuals, physical labels, spare analog tools, and people who understand why the system works, not just which screen to tap. A civilization on the moon cannot be run entirely by black boxes. Black boxes are hard to fix when the nearest replacement is hundreds of thousands of kilometers away. Timekeeping itself becomes strange. A lunar day lasts about 29.5 Earth days from sunrise to sunrise. Human bodies evolved around a roughly 24-hour rhythm. A colony would probably keep Earth-like working days inside, but the outside world would not match. For 2 weeks, the sun may crawl across the sky. Then 2 weeks of night may follow in many regions. Near the poles, lighting patterns become more complicated, with long shadows and changing illumination on ridges and crater rims. Inside, clocks may say morning. Outside, the sun may barely move. That separation between biological time and environmental time can affect sleep, work, agriculture, maintenance, and mood. Artificial lighting can help. Schedules can help. But again, help means equipment. A broken lighting system is not just inconvenient if people depend on it to sleep, grow food, and stay mentally stable. The moon also challenges the idea of privacy. On Earth, privacy can mean closing a door, walking outside, or disappearing into a city. In a habitat, every person is also a heat source, a carbon dioxide source, a water user, and a biological organism sharing air with everyone else. The system may need to monitor movement, health, consumption, and location for safety. That can save lives, but it can also make residents feel constantly watched. A colony needs privacy without losing situational awareness. That is hard. Medical information matters in a closed environment. Mental health matters. Substance use, infection, fatigue, and conflict matter. If one person's behavior can endanger the habitat, the community may demand more monitoring than would be acceptable on Earth. But if surveillance becomes too heavy, the colony becomes psychologically hostile, even if mechanically safe. The moon compresses freedom. It does not eliminate it, but it forces every freedom to negotiate with survival. Scientific preservation creates another tension. The moon is valuable partly because it is ancient and quiet. Its surface preserves impact history. Its far side may offer extraordinary radio astronomy. Its permanently shadowed regions may hold chemical records from billions of years. Human activity can disturb those records. Exhaust plumes can deposit material. Landers can throw dust. Rovers can contaminate pristine regions. Mining can destroy information before scientists fully understand it. A colony that treats the moon only as a construction site may erase what made the moon scientifically precious. That does not mean humans should never build there. It means building must include protected zones, careful approach paths, contamination standards, and respect for historic and scientific sites. The moon is not alive, But it is not empty of value. Some places may need to remain untouched because they are records, not resources. This is especially important near water ice deposits. The same permanently shadowed craters that attract engineers may attract scientists for different reasons. Ice can tell a story about comet impacts, solar wind, ancient volatiles, and the movement of molecules across the lunar surface. If mining begins too quickly, the record may be mixed, heated, polluted, or removed. A future lunar society might have to choose between using a resource and studying it first. That choice is not simple. People need water to live. Science needs preservation to understand. Industry needs access to grow. Governments may want strategic control. Companies may want profit. Environmental ethics on a lifeless world may sound strange, but the moon will force humanity to invent them. The question will not be whether the moon has nature in the Earth sense. The question will be whether every untouched place automatically becomes available once humans can reach it. The answer will shape the character of lunar settlement. If the first generation behaves carelessly, later generations may inherit a damaged archive. If the first generation freezes every useful site, in the name of preservation, settlement may remain too limited to survive. Balance will be difficult, and the balance may change as technology improves. Another practical issue is transportation. A colony spread across useful sites will need rovers, paths, navigation, emergency shelters, charging points, and rescue plans. The terrain is not a flat grey floor. It includes craters, slopes, boulders, ridges, soft regolith, deep shadow, and lighting conditions that can hide hazards. A rover route that looks short on a map can become slow and dangerous when visibility, slope, dust, and communication are considered. A vehicle breakdown on Earth can mean waiting by the road. A vehicle breakdown on the moon can mean calculating oxygen, temperature, battery life, suit endurance, and rescue distance. Pressurized rovers reduce the risk, but they become small spacecraft on wheels. They need seals, thermal control, air, power, navigation, and maintenance. Unpressurized rovers are simpler, but they expose crews to suit limitations and radiation. Every journey outside the base becomes a mission. That changes the geography of daily life. Places are not measured only by distance. They are measured by risk. A crater 2 kilometers away may be close in a human sense, but far in operational terms. A ridge with sunlight may be valuable but hard to reach. A shadowed ice deposit may be essential but dangerous enough to require robotic work before humans enter. The first lunar maps for settlers will not be tourist maps. They will be risk maps. They will show safe paths, dust danger zones, communication shadows, thermal shelters, emergency caches, power links, rover charging points, slope limits, radiation shelter access, and landing exclusion areas. The colony will gradually turn wilderness into infrastructure, not because the moon changes, but because humans mark the few ways through it that do not kill them. Then, there is the question of scale. A small outpost can be kept alive with careful planning. A large colony needs families, workers, technicians, teachers, cooks, doctors, farmers, engineers, miners, pilots, scientists, mechanics, administrators, and children. It needs people who are not all elite astronauts. That is when the environment becomes more difficult. Systems designed for highly trained crews may not work for a broader population. A true settlement must be safe for ordinary people on ordinary days. That does not mean risk-free. No society is risk-free. But the risk has to become understandable, managed, and acceptable. If every resident must think like a test pilot, the colony cannot grow into a city. If every hallway feels like a spacecraft checklist, daily life may become exhausting. Engineering must eventually hide some complexity without creating ignorance. This is one of the hardest transitions. From mission to town, from crew to community, from survival procedure to culture. And culture may decide whether people stay. A child raised on the moon might not experience the place as a prison. The low gravity, black sky, indoor gardens, quiet corridors, and Earth hanging overhead could feel normal. Earth itself might become the strange place, heavy, noisy, wet, windy, biologically overwhelming. That is both fascinating and unsettling. Colonization does not only move humans into a new environment, it may create humans whose idea of home changes completely. That future is not necessarily bad, but it is not simple. If lunar-born people become medically, culturally, or economically different from Earth-born people, the colony is no longer just an extension of Earth. It becomes a society with its own interests. Those interests may not always match the governments or companies that founded it. The moon might begin as a project and become a political actor. That possibility is far away, but the seeds are planted early. Who controls education? What history is taught? What holidays are celebrated? What language dominates? What happens when local needs conflict with Earth contracts? What rights do residents have if leaving is difficult? What does citizenship mean when home is not a nation on Earth, but a pressurized settlement on another world? The moon turns engineering into civilization. That is why colonizing it is so much more than a technical challenge. It asks whether humans can build not just a base, but a society that stays humane inside an environment that is not. This brings us to the real question behind the title. Is colonizing the moon terrifying because it is impossible? Probably not. It is terrifying because it may be possible, but only if we stop pretending that closeness means safety. The moon is near enough to tempt us, near enough to visit, near enough to see with our own eyes, and near enough to become a target for ambition. Yet the surface itself remains a vacuum-baked, radiation-exposed, dust-covered, low-gravity world where every breath must be manufactured. That combination is dangerous. If the moon were obviously impossible, it would stay a dream. If it were easy, it would simply become the next frontier. But it is neither. It is possible enough to attempt and hostile enough to punish every shortcut. The best path forward is not fear, it is humility. Robots first, where they make sense. Careful mapping, honest testing, small habitats before towns, landing pads before heavy traffic, power systems before permanent crews, dust mitigation before expansion, radiation shelters before long stays, medical autonomy before families, closed-loop life support before large populations, laws before conflicts, rescue plans before emergencies. A real lunar future would be built in layers. First, short visits, then longer missions, then surface infrastructure, then resource demonstrations, then small semi-permanent crews, then larger habitats, then industry, then perhaps families if biology and ethics allow it. At each stage, the moon would teach lessons that cannot be fully learned from simulations. Some lessons will be expensive. Some may be painful. The hope is that they do not have to be fatal. If humans ever build a true settlement there, it will be one of the most extraordinary achievements in history. Not because the moon is far, but because it is close and still so hard. It will prove that humanity can create a living system beyond Earth, even on a world without air, weather, rivers, soil, or protection. It would also teach us what space settlement really means. Not escape, not instant freedom, not domes under a pretty sky. Space settlement means dependence on engineering so deep that engineering becomes part of daily life. It means carrying Earth's habits into places that do not support them. It means learning that a world can be nearby and still alien. The Moon is not a backup Earth. It is the first exam. If we fail there, Mars will not become easier because it is farther away. If we succeed there, success will not mean we defeated the Moon. It will mean we learned how to cooperate with a place that gives almost nothing for free. That is the terrifying problem with colonizing the Moon. The problem is not just getting there. It is staying there without forgetting what the place is. A dead world can host life only if life brings everything it needs, protects it constantly, and accepts that home is no longer something found under your feet. Home becomes something maintained, something measured, something repaired, something shared. On Earth, the planet does most of that work for us. On the Moon, we would have to do it ourselves. And if we ever manage it, the first true lunar city may not look like the future people imagined. It may be buried, quiet, cautious, crowded with machinery, and surrounded by warning signs. But inside, someone may wake up, breathe clean air, drink recycled water, check the power report, look toward Earth, and begin another ordinary day on a world that was never meant to be ordinary. That is when the colony becomes real. Not when the first flag is planted, not when the first module lands, not when the first headline says, "Humanity has returned." It becomes real when people can live through thousands of ordinary days in a place where ordinary life should not exist at all.